Hey everyone, I wanted to make a video about last week's assignment about categorical variables, and we're going to do all 4 questions from last week. This was a compilation of 4 different old AP questions, and some of this stuff might appear on the 2020 exam this year, some of it might not, so I wanted to talk about some of the overarching things and talk about some of the things that I noticed people were doing really, really well, and some things not quite as well. So this is a kind of an overview of what you can see with categorical variables, and many of these things were really good responses. So I wanted to go over some of those, make sure you have the right answers, and let's start in here. So this first question was from 2003, kind of older. It was from the Form B exam, and it was number 1. Students did a really nice job with this one. Not a whole lot of issues with it, but sometimes there's just little silly mistakes with miscalculations and stuff. So the first part that you'll notice, it's basically just a straight probability calculation, just kind of reading it, and it asks for the percentage of people that are in the 31 to 45 age group. So our random sample here, you'll see the 89 out of 207. So again, you don't have to use notation if you're not sure about it, but essentially just capital P, probability, and then describing what you're finding the probability of, and it's just right in the table. 89 out of 207, perfectly great to leave it as a fraction. If you like the decimal version, it was 42995. Either one's okay. And yeah, part A is pretty straightforward. Similarly with part B, this is one where sometimes people do get the condition flipped. It mentions it here. You have this condition of people who are over the 50,000. So a lot of times people use the wrong condition, but the over 50,000 is what it's isolated out of. So you can ignore everything in the chart except this column, and you'll see like the total here. You got the 96 people that are in this annual income, and now I just want to focus on the 31 to 45 age category. So out of these 96 people, let me write the notation. This is the probability of being 31 to 45 given a 50,000 plus salary. And again, you can leave it as a fraction. The decimal comes in kind of handy actually just for part C, not so much with part B. The fraction's the 35. There it is, 35 out of the 96 people, and that is 36.458% or 0.36458. And then the last part, and this is really common with AP questions sometimes, where it'll ask you a couple probabilities, and then it'll ask you to use your calculations from part A and B to make a conclusion. And what I noticed, a lot of students' responses is really good job. It's really important though to make sure, like this part is really important and vital. So you can't just say no and not be explicit about why it's no. So you should say no, that's part of the getting full credit here. No, they're not. But you got to write something about from these calculations in part A. Since the probability of being 31 to 45 is 0.42995, and the probability of 31 to 45 given this age group, or sorry, probability of this age group given this income level is, well, not 42995. It's quite a bit lower actually. So what we sort of see in these 2 calculations is that, you know, the probability of someone being this age is about 43%, but if you just look at the people who make 50,000 plus, the probability that they're in that age group decreases. So what that tells us is that this income level, or in general, all these income levels, will have an impact on how old a person is. Essentially, and what you can kind of really dive in here is that the older a person is, typically the more money they'll make, and that's kind of what you're seeing here too. So since we see that here, we just got to really be able to say yes, or no, there's not an independence between the age group of 31 to 45 and where is it here? And the 50,000 plus salary. So using these answers, we can show independence, and that was this first question here. And again, that was from 2003, number 1. The second question. And I'm just going to flip to the next page here. I know it kind of starts, I cut off a little bit at the top here, but the problem next here was from 2011. It was number 2, and it's actually almost identical to that question that we just looked at. There's definitely a little bit of differences here, and what I noticed is people did really, really well with part A and B, but when it got to part C, saw quite a few more mistakes there. But the first part was reading the table again and looking for a specific probability. This one is, again, it's conditional, so it's a little bit different than the first one, but just reading carefully. This one's usually not too difficult. Given that a randomly selected registered voter is male, so we're just really looking at this 200, or the sample of 200 people here. What is the probability that he's registered for party Y? So you really just have this 200, and out of these 248 of them are in party Y. So the probability that it's from party Y given male is 48 out of 200. And you can again leave it as a fraction if you like. If you prefer the decimal, that's okay too. 24%. And then the next question is jumping right into this idea of independence between these two events, male and registered, or for party Y. So to confirm this one, what I'd want to check, the easiest way, is use this answer from part A and compare this number, this 24%, to just the overall group itself. Like, what is the probability that a person's in party Y in general? And if that condition, if the male condition doesn't change the probability of being in party Y, then what we would say is, well, the gender makes no difference on a person being in party Y. What we'll see in this case, if we just look at party Y here, we got 168 out of the 500 people total, and this decimal is definitely kind of a nice comparison, easier than the fraction. It's a little over 33%. So what we have to be able to do here is justify if these two things are independent or not. So same thing from the last task, but we want to be able to say they're not independent, and we can use the justification of the probability changed when we put a condition of male on it. So we just got to make sure we're really explicit about that. So justify your answer based on the probabilities calculated from the table above. So we want to say something like no, and again, some of that same reasoning, since probability of Y, I'll do that a little more clearly. Probability of Y does not equal the probability of Y given male. These events are not independent. These events are not independent. And I'm kind of squeezing these tasks, or this writing here on the side. That would have probably been better if I'd just written it on a separate sheet of paper, but I'm just squeezing them in the margins here today. Where the task got kind of a twist on it from before, and seemed to be one of the more challenging tasks, was this new township. So this first data set was from Franklin Township, and what they give here is this display of Franklin Township. So what this represents is this exact same table, just in a segmented bar graph. So where these numbers are coming from are, let's take this number here for a second. So this number, this segment, is the females that are in party W. So if you just focus on this top row, 60 out of 300 are female in party W. So 60 out of 300, and that number is 20%. That actually lines up with this 0.2 down here. This next party X, where that number came from, was 120 out of 300, and this final one was also 120 out of 300, and in each of these cases these are both 40%. So that's where these numbers are coming from. And what we just did in part A and B in a roundabout way, not directly, but we sort of show that the gender makes an impact on the probability of a person being in party Y. So what that tells us, this graph shows us the same thing we just calculated actually, is that what we saw in general from party Y, this is from part B, the probability of being in this party in general is about 33.6%, but if you just look at the males, it's only 24%. So basically what this 33.6 is, it's a combination of the male and female, but if you isolate out the genders, you're going to get different values. So what independence would give us is there wouldn't be this difference. So this long way of me saying, like, when they finally ask us about Lawrence Township, and I say, well, this other town has the same breakdown for parties W, X, and Y, but what it is different about it is that they are independent. So what should happen in this display, and you get this, here it is up here, you get this display up here that you just have to fill in, and how you fill that in is really only based on if these things are independent. So you can ignore these gender breakdowns and just look at the totals. So if in Franklin Township we see this party W here is 88 out of 500, I'll put that up here. So party W is 88 out of 500, which is 176. So almost 17.6%. So I'm going to look back at this Franklin Township for a second. I didn't show you this one earlier, but where this number came from was the males who are in party W, so this as a fraction would have been 28 out of 200, which is 14%. So the 17.6 is kind of, it's not an exact average of these two numbers because there's a heavier weight in the female group than there's the male group. But this this idea that if they're independent, it's kind of got to be an average of these two, a weighted average. So for this graph, what we want to be able to do is figure out, well, if they're independent, then they have to have the exact same probability of happening. The gender won't make a difference in a person being in party W or not. So both of these, let me put this as W here, percentages are going to be equal. And then the same thing's going to happen for party X. So you can ignore the gender breakdown again. You'll see that there were 244 out of 500. But if they're independent, then basically both male and female are going to have that same proportion. So the probability of party X, 244 out of 500, that value is almost 50%, 48.8. And I want to draw my line so that it's going to have 48.8%. Basic, you know what I'm going to do to get that line a little more accurately? I'm going to actually get the probability of party Y first and then work from the back end here. So the probability of party Y, we had that number from before. It was 24%, sorry, 33.6%, 168 out of 500 is 33.6. So that line, 10, 20, 30, about here somewhere. So this is 336, 336. And again, the whole point of this display is that if things are independent, the gender won't have any difference on the probability of the parties. So that's what should happen in this particular display. Many students actually just recopied the display from Franklin Township, and that's incorrect response. What you have to do here is just use the totals from the parties from the previous town. So that one was definitely a little more challenging. This really gets at the concept of what an independent event means. So I like that question a lot. It's kind of a different way of making you think about independence. So that one was definitely a little bit trickier. But those first two questions in general had similar themes, where you have this table and you create probabilities and then look for this independent concept. Where the next two questions, actually, they have some similarities, but there's one massive difference in both of them. They also get at the concept of a hypothesis test. So I wanted to show you what those questions look like. And this one here, this number 3, this one came from 2009. It was number 1, is about part-time jobs, and also broken down by gender. And what they asked to do first, this was from number 1 from 2009 again. And I actually already pre-made the display just to save a little bit of time. So I'm going to show you a couple of different ways you could have done this. This one here is called a bar graph, and categorical data you can make bar graphs for. So what I've done in this case is just broken down by gender, the groups that are in never. So how I drew this line up here is I just looked at the never group. There were 52 people that never had a part-time job. Out of those 52, 21 are male. And out of those 52, 31 are female. So that's all I did here, just divided my calculator. It's a little bit above 40%. So just sketched it out. And same thing with only summer jobs, just focused on the 28 people that were in that group. This was a little closer to 50-50. And then the last group was not only summer jobs. So there were 20 in that group, 12 male and 8 female. And I want to show you another display before we look at part B. So it's also very possible, if you preferred, you could have switched this around and just had the axis down here, just have 2 of them. You could have one for male, one for female, and then you'd have 3 bars. You could have a bar for never, a bar for only summer, and a bar for not only summer. That would be a perfectly fine display to use here as well. But the other display that I made ahead of time it's similar, but it's got a different name. It's just a little bit different look to it. It's called a segmented bar graph. And what a segmented bar graph is essentially the same thing. It's just that they stack. So what will happen in these cases is they'll add up to 100% every time. So I actually switched my condition on this one. On the way I made the first display, I put the conditions based off of the type of job. And I have to label my axis. So this is the percent of gender by job. Never, only summer, not only summer. And the other one, I just decided to flip just for a different visual. So this one is the percentage of job experience conditioned by the genders. So these denominators, they're a little different because the male, there were only 48 male. 21 of them never had a job. So I divided those 2 numbers out. I forgot what the number was actually. A little over 43%, I want to say. And sort of drew my line up to that spot. And then the difference here is it just stacks. So the 15 out of 48 males only had summer jobs, and then the 12 out of 48 had not only summer jobs. Same thing with the females. And the purpose of both of them is just to really be able to do part B accurately. And either display would work great to do part B. Basically, all you have to do with part B is just compare, and like I said, either of these displays would work. You definitely wouldn't have both. You just have to compare every proportion within every subgroup. So if I'm using this display, I'm going to write something like the proportion of female who never had a part-time job is higher than the proportion of males who never had a part-time job. The proportion of females who only had a summer job is a little bit, I think that's a little bit less actually, than the proportion of male jobs. It is a little bit less. I wish I'd have written the decimal version. And then if I have the specific values there, I could use those specific values. If I want to not use those specific values, I could also say that as well. But I just have to compare I could do this in 3 sentences. A sentence for each job experience. One for never, one for the only summer, and one for the not only summer. And if I happen to have this display in front of me, I want to do the exact same thing. I just want to be able to compare and write about within the never group, there's a more likely chance that that person is female. And again, you can compare the 2 proportions, but just write a sentence for each one of these things. That's all we got to do. So they're actually pretty easy to describe. I'm talking about part B here. Write a few sentences comparing what these displays in part A show you. And really, every time and we'll see one in number 4 as well, all you got to be able to do is just write a sentence about each one of those things. It's not quite as complicated, not that the SHOCKS acronym is complicated, but it's not like that. We have to worry about shape, center, spread, and outliers. All we got to be able to do is just compare the 3 bars, or 6 bars, I guess, in this case. And that last question with this one here, it says which test of significance should be used to test if there's an association between gender and job experience. So what I wanted to, and this is sometimes used as independence actually. So what I wanted to describe here, independence, easy for me to spell. So when you get a question like the one we just had, and it asks about a specific two events, like male versus party Y, that's the calculation where you just do, well, I'll bring it back up here, right here. So if you just have to check for the 2 events, you can compare these 2 probabilities, and that's it. But there was also, and this is the stuff that was cut from the exam, so this kind of question should not appear in the exam this year, but there is a test for significance to doing these things, and it's not a single calculation. It actually tests the whole, where did I put it in here? It tests this entire gender category versus this entire job experience category. So these 2 different categories, and you can do a test. It's called a chi-square test for independence. And since it's not on the exam, we never really talked about it in class before we got on this at home situation. So I want to just show you what that would look like. They're actually not that difficult to do. So we don't have to actually perform the test here, but I did want to at least give you the answer to this one. So the null hypothesis and the alternative hypothesis kind of a lot of similarities. And this is definitely one that you need to do in words. Basically, you'd want to write something like this. There is no association the assumption is that there's no association between gender and job experience. And then the alternative hypothesis will be something just as simple. There is an association between gender and job experience. So the null and alternative hypothesis, you assume that there is no association, and then you go through and you calculate. It's called the chi-square statistic, and then if that value comes out to be significant, basically we'd check its p-value, and then we'd make our conclusions. But none of that stuff's on the exam this year, so we don't have to worry about being able to do those tests. But I just wanted to talk about what the answer to part C was, and the same thing kind of happens in this last question, so I put them at the end. And speaking of that last question, similar again. It starts out with scroll down here a sec. So with 2014 number 1, this one's a little more recent. It's actually kind of similar to the one we just looked at. There's a little write-up about these different students, whether they live on campus, whether they live off campus. The big difference, it's a little bit quicker, I thought, than the previous one, because you don't have to make a display. So you get this data set here, and one of the massive differences, you don't have to create that display. So they give you the display down here. I did get some calculations before I got on here just to make it a little bit quicker. But what the part A is getting at, it says calculate the proportion of on-campus students in the sample who participate in at least one. So I saw sometimes people make the mistake of not doing at least one. So when it says at least, we got to do a little bit of addition here. So on campus, we have to include the 17 and the 7 more who do 2 or more activities. So it's a sum of those two values. So for the on-campus proportion, there's 33 students who are on campus. 24 of them have at least one extracurricular. And very similar, got to add these two numbers up. So there's 37 out of the 67. That's 552. I didn't get the decimal for that other one. It was 7272 repeating. So on campus, quite a bit higher proportion of people who participate in at least one extracurricular than the off-campus proportion. And what the second prompt gets to is writing a few sentences again. And this question is not very difficult. It's basically that you have to write a sentence comparing each of these things. So if you write, you can give the specific numbers here, but you could say something like the proportion of students who do not participate in any extracurricular activities is higher for the off-campus than the on-campus group. For one extracurricular, it is higher for the on-campus group compared to the off-campus. And again, you can give the specific numbers. In this case, I find it kind of easy to just write down the percentages in this case. It's not required for full credit on these responses, but essentially you just want to compare. So it's really just 3 sentences. And you have to do all 3 to get full credit, and sometimes people leave one off. But basically just write a simple sentence about comparing each of the 3 subgroups here. And then with part C, the last one, it's really similar to the last part C we had. It says after verifying the conditions for inference were satisfied, the administrator performed a chi-square test of the following hypotheses. There's no association between residential status and extracurricular activities. So again, there's a little bit of a difference between doing a hypothesis test between the whole table, and this is a sample of a larger population. So what hypothesis test will do is determine if there's evidence that these two categories are independent, not just a specific event. So that's the stuff that was cut, but how it looks in hypothesis test form is down here. In this question, while not something that we would have done yet, interpreting a p-value, you can do this without knowing anything about these two hypotheses, or even just how it was calculated, because we know how to interpret p-values. This number is not significant you can pick your level. You could say even 0.10. So what that must mean is there's not enough evidence to reject the null, and we could say something like there's not enough evidence to say there is an association between residential status and level of participation in extracurriculars among students at the university. It's as simple as that. So while we haven't talked about how to get this number and where it would have come from, we actually don't need it to know how it got calculated to interpret it. So we could just say something like there is not enough evidence to say there is an association between, and I'm just going to underline it. I would just write these exact same words down. I'm going to do that pretty much every time we do a hypothesis test. Just use your null and alternative hypothesis, put it back in context, and it's already written here, so I would just write the exact same sentence. So now there is not enough evidence to say there is an association between residential status and level of participation in extracurricular activities among the students at the university, and that would be it. So these 4 questions were the theme of last week, and big concepts, being able to read categorical data, those are usually pretty easy tasks, and find some probability of those categorical data, and then sometimes you have to find if 2 events are independent or not. And then the stuff you don't have to worry about is finding if the entire category of gender, or in this case on campus, off campus versus extracurriculars. We don't have to worry about the entire categories. What we'll have to just be able to do perhaps is just find if 2 events are independent or not. So I wanted to go over those. Feel free to make some comments or shoot me some questions, and I'll try to answer those as best I can. So thanks for checking this out, and have a good one.